The launch of the James Webb Space Telescope, JWST, is a monumental achievement in the field of astronomy and space exploration. Developed by NASA in collaboration with the European Space Agency, ESA, and the Canadian Space Agency, CSA, the state-of-the-art observatory is designed to be the most important observatory of the next decade, serving thousands of astronomers worldwide. JWST's mission is to study all stages of the history of our universe, from the first bright flashes after the Big Bang, to the formation of solar systems capable of supporting life on Earth-like planets, to the evolution of our own solar system. The JWST concept began in the 1990s, shortly after the Hubble Space Telescope, HST, began producing groundbreaking images and data of the universe. The Hubble Space Telescope gave humanity the first detailed view of the cosmos, capturing stunning images of distant galaxies, nebulae, and star clusters. However, scientists and engineers realized the need for a more advanced observatory that could look ever deeper into space and time. JWST was developed to meet this need, with the goal of expanding our understanding of the origin and evolution of the universe. Developing the JWST was a huge engineering challenge. The telescope had to be equipped with a much larger mirror than Hubble's to catch more light and see into the distant universe. The diameter of JWST's main mirror is an impressive 6.5 meters compared to Hubble's 2.4 meters. That increased size presented major challenges to its launch and deployment, as the mirror and massive sun shield needed to protect it from the sun's heat had to be folded up to fit inside the launch vehicle and then fully deployed in space. The main scientific goals of JWST are to search for the first galaxies that formed after the Big Bang, to learn how galaxies have evolved from birth to the present, to trace the formation of stars and planetary systems, and to measure their chemical properties of planetary systems, including our own solar system, and to explore the possibility of life in those systems. One of JWST's most exciting goals is to observe the first galaxies that formed after the Big Bang. These galaxies are incredibly distant and dim, making them difficult to detect with current technology. JWST's infrared capabilities are critical to this mission because the light from these early galaxies has shifted into the infrared part of the spectrum due to the expansion of the universe. By studying these early galaxies, scientists hope to gain insight into the conditions of the early universe and the processes that led to the formation of stars and galaxies. JWST also plays an important role in understanding the evolution of galaxies throughout the history of the universe. By observing galaxies at different stages of their development, astronomers can piece together the birth story of galaxies like our own Milky Way. JWST's ability to see through dust clouds and observe the infrared light emitted by stars and galaxies provides a clearer picture of the processes that lead to galaxy evolution, such as star formation, mergers, and interactions with the intergalactic medium. The formation of stars and planets are complex processes that are not yet fully understood. JWST helps solve these mysteries by observing the regions where stars and planets are currently forming. These regions, often obscured by dust and visible light, can pass through JWST's infrared vision, allowing scientists to see the intricate details of the birth of stars and planetary systems. By studying these processes in different environments, astronomers can gain insight into the factors that influence the formation of stars and planets and the diversity of planetary systems. JWST is also a powerful tool for studying exoplanets, planets that orbit stars in our solar system. One of the most important features of the telescope is its ability to analyze the atmospheres of exoplanets by studying the light that passes through them when the planet passes in front of its host star. This allows scientists to determine the composition of their atmospheres and look for signs of habitability, such as the presence of water vapor, oxygen, and other life-related molecules. By studying a variety of exoplanets, from Earth-like planets to gas giants, JWST helps us understand the diversity of planetary systems and the possibilities for life outside our solar system. The design and construction of the JWST is a triumph of modern engineering. The primary mirror of the telescope, which consists of 18 hexagonal segments, is covered with a thin layer of gold to improve its reflection in the infrared spectrum. Each segment can be individually adjusted to achieve the precise optical alignment the telescope needs for proper operation. The mirror is protected by a multi-layered solar shield, about the size of a tennis court, which blocks heat from the sun, Earth, and Moon, allowing the telescope to operate at the very low temperatures required for infrared observations. Deploying JWST was a very complex process. After launching from an Ariane 5 rocket from French Guiana, the telescope went through a series of carefully choreographed steps to open the mirror and sunshade. This involved separating the 5 layers of the sun visor, positioning the secondary mirror, and aligning the primary mirror segments. Every step was critical, and every failure could jeopardize the mission. The successful deployment of JWST was a testament to the careful planning and engineering expertise of the teams involved. Since its launch and deployment, JWST has already begun to revolutionize our understanding of the universe. One of his first major achievements was taking stunning images of the Carina Nebula, a region of active star formation. These images revealed intricate details of the nebula's structure, including previously hidden stars and protostars. JWST's observations of the Carina Nebula have provided new insights into the processes that influence star formation and the effects of massive stars on their environments. Another important discovery was the detection of water vapor in the atmosphere of an exoplanet called WASP-96b. Hot Jupiter, about 1,150 light-years from Earth, was spotted during the transit, allowing JWST to analyze the starlight passing through its atmosphere. The detection of water vapor was a crucial step in understanding the composition of the atmosphere of an exoplanet and showed the potential of JWST to study the habitability of distant worlds. One of the most surprising discoveries came from JWST's deep exploration. Focusing for a long time on a small, seemingly empty patch of sky, the telescope captured thousands of galaxies, some of which formed only a few 100 million years after the Big Bang. These observations showed that galaxy formation occurred much earlier than previously thought, and that some of these early galaxies were surprisingly large and mature. These findings challenge existing theories of galaxy formation and suggest that the early universe was a more dynamic and complex place than scientists imagined. JWST's early findings have profound implications for our understanding of cosmology and galaxy formation. The detection of massive, mature galaxies at such an early stage suggests that the processes that drive galaxy formation may be more efficient than previously thought. This challenges the standard model of cosmology, known as the lambda cold dark matter (LCDM) model, which predicts a slower, more gradual formation of galaxies. One possible explanation for these unexpected findings is that the universe experienced rapid star formation shortly after the Big Bang, known as the cosmic dawn. This era saw the formation of the first stars and galaxies, which began to ionize the universe, making it transparent to ultraviolet light.
JWST's observations of early galaxies provide crucial information for understanding the timing and duration of the cosmic sun and the processes that led to its rapid star formation. Another possibility is that new physical phenomena or exotic forms of matter may be needed to explain the early formation of massive galaxies. For example, some scientists have suggested that the universe may have been born with supermassive black holes that caused the growth of early galaxies. Alternatively, new forms of dark matter or dark energy may have contributed to the acceleration of structure formation in the early universe. These ideas are still speculative, and further JWST observations are needed to test these hypotheses. JWST observations will also influence our understanding of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter, which makes up about 85% of all matter in the universe, has not yet been directly observed. Its existence is due to gravitational effects on visible matter and the cosmic microwave background. Despite extensive searches using various observational methods, the particle or particles that make up dark matter remain unnoticed. JWST observations of the distribution of galaxies and their dark matter halos provide new information for studying the properties of dark matter. By mapping the distribution of dark matter in the early universe, scientists can test different models of dark matter and gain insight into its nature. JWST's ability to observe the gravitational lensing of distant galaxies within dark matter halos also places new constraints on the properties of dark matter. Dark energy, the mysterious force driving the accelerated expansion of the universe, is another focus of cosmological research. The inclusion of a cosmological constant, lambda, in the LCDM model to account for this accelerated expansion led to the cosmological constant problem. Quantum field theory predicts a much larger value for lambda than has been observed, leading to an important contradiction that remains to be resolved. JWST observations of distant supernovae and the large-scale structure of the universe provide new information for the study of dark energy. By measuring the expansion rate of the universe at different epochs, scientists can test different models of dark energy and gain insight into its properties. The JWST observations also help refine the measurement of the Hubble constant, a key parameter that describes the expansion rate of the universe. JWST is expected to operate for at least 10 years, and its mission may be extended depending on the availability of fuel to maintain the station. During this time, it will conduct a wide range of observations, from deep field surveys to detailed studies of individual objects. Data collected by JWST will be made available to the global scientific community, allowing scientists to conduct their own research and make new discoveries. JWST's success also paves the way for future space telescopes with more advanced capabilities. One such mission is the Rome-based Nancy Grace Space Telescope, formerly WFIRST, which is expected to launch in the mid-2020s. The Rome Space Telescope will conduct large-scale surveys of the universe, complementing JWST's detailed observations with its wider scope. They also study the nature of dark energy and search for exoplanets using microlensing techniques. Future space telescope concepts include the LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, missions in the long term. These telescopes are designed to study a wide range of astrophysical phenomena, from the formation of stars and galaxies to the search for habitable exoplanets. Lessons learned during the development and operation of JWST will inform the design and construction of future observatories, ensuring that they continue to advance our understanding of the universe. In addition to its scientific achievements, JWST has had a major impact on the general public and the field of astronomy. The stunning images and groundbreaking discoveries made by JWST have captured the imagination of people around the world and inspired a new generation of scientists and engineers. The success of the telescope also emphasized the importance of international cooperation in space exploration. With the help of NASA, ESA, CSA, and countless scientists and engineers around the world. JWST data is also used for educational purposes, providing teachers and students with access to real-world scientific observations. Educational programs and outreach use JWST discoveries to teach concepts in astronomy, physics, and engineering, promoting an understanding of the wonders of the universe and the importance of scientific research. The James Webb Space Telescope is a monumental achievement in astronomy and space exploration. Its advanced properties and early discoveries have already begun to change our understanding of the universe, challenging existing theories and opening new avenues of research. As JWST continues its mission, it will provide unprecedented insights into the origins and evolution of the cosmos, from the formation of the first galaxies to the possibility of life on distant exoplanets. JWST's success is a testament to the dedication and expertise of the scientists, engineers, and organizations involved in its development. It also underscores the importance of continued investment in science and space exploration as we seek to answer some of the most fundamental questions about our place in the universe. JWST is not just a telescope. It is a symbol of human curiosity and ingenuity, a beacon in our quest for knowledge that will illuminate the cosmos for years to come.